Welcome back. We will continue our discussion on the linear stability analysis which we were performing for trying to understand the spontaneous instability of an ultra thin liquid film. You may recall that in the previous class we were doing the derivation. So, we were looking at the order of magnitude analysis of the governing equation and incorporating the appropriate conditions, which include the kinematic boundary condition and other conditions that we have been looking in. So, we have reached up to this stage. So, this is a quick recap we would like to do. So, we started off with the continuity equation and the x and y component, x and z component Navier-Stokes equation, understanding or plugging in our concept of a fluctuating interface instead of a completely flat interface. And we also derived two classes before the condition of the kinematic boundary condition, which takes care of the surface fluctuations or non-zero interfacial velocities. And once we started looking into, so these are the set of equations that we have looked into, continuity, the x and z component Navier-Stokes equation along with the Young-Laplace equation for an axis symmetric surface, simplified for the long wave approximation, and this is the kinematic boundary condition. We started to do an order of magnitude analysis. We just discussed briefly what an order of magnitude analysis is, and that eventually showed us which are the relevant and which are the non-relevant terms. And finally, this is the form of the final governing equation which we obtained from the x component Navier-Stokes equation. Okay. We also obtained dP, P is the non-gravitational pressure, dP dz is equal to 0 from the z component Navier-Stokes equation, and then we started to work with the governing equation for the system, started to integrate it with appropriate boundary conditions, and which has finally led us to this particular point, which gives us del h del t is equal to 1 by 3 mu h cube p x x in a conservative form. We also understand that P is a function of pressure plus phi. Now, this pressure, if we are considering the liquid surface, had the film been perfectly flat, the pressure right at the surface on the liquid side, PL or PS or whatever you want to write, and let us say this is the P outside or PB. So, had this film been and perfectly flat, then we know that the surface been in mechanical equilibrium, then Pb would have been equal to Pl. But now that we understand that we have surface fluctuations, which means that the surface is no longer flat. Therefore, Pb is not equal to Pl anymore. In fact, Pb, okay, let us draw it separately. So, this is the situation we have, this is the equation up which we have derived up to this point. Anyone who has a confusion about the origin of this equation or is joining late, please refer to the previous couple of lectures, which gives you a very clear idea about how this equation comes. Now, we argue that P is equal to, or we understand P is equal to P plus phi. We are now looking at this P at the interface. So, over here. So, let us say that this is PS and this is PB, Since the liquid is not flat, the film surface is not flat, therefore, Pb is not equal to Ps. And Pb and Ps are interrelated through the Young-Laplace equation. Okay. If the film is exposed to atmosphere, then of course, Pb is equal to 1 atmosphere and is equal to constant. So, what we have for the situation where a small slope approximation is valid, that is Hx is equal to 0, we have delta P, which is Pb minus Ps. I mean, this is equal to gamma into Hxx. This is the convention. So, Pb minus Ps. So, do not confuse the signs. So, it remains like this. Therefore, okay, it gives us Pb equal to gamma into Hxx. Let me just quickly remind that for an axisymmetric surface, this is the complete expression for the Young-Laplace equation. And if we assume that the nature of instability is long wave, that is h is much larger than x, then of course, one gets Hx is close to 0, and therefore, once you substitute that, you get to this form of the Young-Laplace equation. Okay. Now, what we get is Ps is equal to essentially P evaluated at z is equal to h, and which is Pb minus gamma Hxx. Therefore, Px, if we differentiate it, so this is essentially you are looking at del del x of Pb minus gamma Hxx. Pb is constant, so what you are left with is minus gamma Hxxx. Okay. Similarly, so this is one important parameter. Now, why we are looking into it is essentially we need to find out an expression for Px in this expression, and we know P is equal to small p, that is the pressure plus phi. So, we need to essentially find out independently Px and phi x, and that is precisely what we are doing, and in doing so you see that we now have an expression for Px. Okay. Now, what is phi? Phi is the essentially it is the interfacial potential and which we have seen that considering the x based on the excess interfacial potential and from an expression of del g is equal to a minus a divided by 12 pi h square, which comes from the considering the interfacial van der Waals interaction, we already have obtained an expression of phi which is 6 pi h cube. But this expression, please remember, it comes from the only from the attractive van der Waals interaction. So, typically this phi is the potential, and in Navier-Stokes equation it includes gravity or let us gravity and other body forces are neglected, or I would say that at this length scale. So, let me put it like this for simplicity, that at this length scale which is of the order of roughly 100 nanometer, we have already argued that gravity and other body forces can be neglected. Of course, you are talking of a situation where you do not apply any externally imposed electric or magnetic field, and that is the reason that they do not show up as body forces. But in cases where you can apply essentially or in principle an electric field or a magnetic field to a thin film to destabilize it. I think we will take it up in one of the last lectures. So, that is what is the situation where the instability is triggered by the application of an external field rather than the spontaneous instability that we are talking here. The only limiting thing about this particular expression, though we will continue our discussion with this expression, is that this considers this expression considers only the attractive van der Waals interaction. Okay. A rather but in reality for an unstable film, phi is made up of antagonistic interactions with different rates of decay. Two major components, as we have already talked, for a general dielectric film are the longer range interfacial van der Waals interaction and rather short range steric repulsion, which in a way we have talked about the hard sphere model and the contact repulsion because of the overlap of electron charge cloud, etc. So, this is essentially steric. So, essentially the molecules are coming in contact with each other and therefore manifests in the repulsion. So, these are the two general terms which are most popular in a general dielectric film. A popular representation of phi for an unstructured thin liquid film that can be used rather well even for a polymer film in liquid form that is heated beyond Tg or exposed to its solvent vapor is given as phi is equal to A s. So, we just write A s for the effective Hamarkar constant for the system, which we already know. Now, this term you can immediately see that this term is corresponds to the interfacial van der Waals term. So, A s is the effective Hamarkar constant. SP denotes the strength of medium or short range interaction with and it is it denotes any medium or short range interaction. It is attractive when SP is less than 0, because SP is less than 0 because yeah. So, and repulsive when SP is greater than 0, and LP represents the corresponding decay length. Okay. This term sort of accounts for the AB type interaction or the polar interaction. So, it is this term for the polar interaction as well as the any entropic confinement effects in a polymer. So, this third term is rather interesting. This is more of an artificial term and particularly included for simulation, which is present to remove any non-physical singularity in the event Sp tends to 0, that is there is no repulsive term present in the system, because as we have already talked about that under the hydrodynamic framework, no study of wetting or dwetting is possible until and unless there is a short range repulsion or repulsive terms are present. So, in the event there are no repulsive terms present in your system physically, you can't run your simulations based on the hydrodynamic framework or based on the way we are performing the analysis, that is considering the Navier-Stokes equation to be the governing equation. So, you need to sort of have something, this is a non-physical singularity, a very local, which sort of is akin to a local contact repulsion or something like that, but that term has to be present. Of course, one has to understand that no study of instability is possible if there is no attractive interaction, or in other words, no not only study, but no instability interaction. So, this is the, you may want to recall that if you plot delta G versus or the force potential versus h, or the separation distance or x or whatever, this is the type of a film which is going to be unstable. So, this part of the system is due to the attractive interaction. In case there is no attraction, there is repulsion all the way, you will get a curve like this, which will represent the film to be unconditionally stable at all conditions. And this is a typical curve for a metastable film, where one can say that this is a critical thickness corresponding to that metastable film, where the film is, so the third curve represents the curve of a metastable film, which is unstable for and stable for h greater than hc. Okay. So, yeah, this is some bit of understanding that we need to have about the expression of the potential, the interface potential, but for our analysis we are looking at the possible origin of instability, which is attributed, as we have already talked, which is attributed to the interfacial attraction, long range van der Waals attraction. That is the only reason of instability we are assuming so far, or in other words, the long range attractive or the attractive long range van der Waals interaction between these two interfaces is the only force that is responsible for instability. That is what we are assuming. So, we will limit or we will consider this expression of or maybe we can write a expression of phi for our analysis. So, coming back to why we started to pick it up. So, we are essentially looking at this particular expression, we have looking at P, and we would like to find out Px, and in order to do that we need Px and phi x. Px we have already done, and we already have an expression for Px which needs to be plugged in into our system, and we also now have an expression for phi, so which we are going to use for our subsequent analysis. So, what we have is this at this point of time is phi is we need to find out del phi del x, which turns out to be del phi del h as phi is a function of h and del h del x. So, which if we now look back at our governing equation, which is del h del t, or the equation where we started our discussion, which now if you substitute the values of phi x and p x, you will get so the expression of p x we already have, which we will simply plug this one in, and of course the expression of phi x is here, and finally what we have is it's if we write this equation in a little compact form, what we will get is h t where as I have mentioned previously also, a suffix refers to differentiation. So, del h del t is essentially h t, so if h t is equal to 0, then one gets a steady state solution however, we know that h is a function of h x, right, and which is essentially a non-uniform steady state, and as it is not flat, which is originates from the origin is the interfacial fluctuations. So, this is essentially a fourth order nonlinear PDE, and it might have infinite number of it actually has infinite number of steady state solutions. So, any h is essentially a solution for this if h t is equal to 0. So, essentially since h is equal to h x, which is the surface is not flat. So, it is essentially a quasi, so steady state solution is a trivial solution essentially here. It is a quasi steady state situation. Okay. Now, one of the major utilities of this particular equation is to test numerically whether a film of initial thickness H0 remains stable or becomes unstable and ruptures with time. Okay. So, in the previous class or couple of classes before, we had shown a video of a spontaneous rupture of a film. So, I just tried to replay it. So, this is what we were talking about. So, what we have done or what we would like to test, that by means of spin coating. So, you have created a film which has a thickness of H0. And qualitatively, we already know several factors that if a film is thinner, then the chances or the possibility of instability is higher, because the two interfaces will be closer to each other, therefore, the magnitude of the interfacial attraction will be stronger, etc., etc. But here this equation gives us the opportunity to quantify that, and in terms, so essentially one can use this equation to test whether a film of initial thickness H0 remains stable with time or not. So, essentially what is done to do that is the film, the initial height H0 is sort of perturbed with a function f, the function of x and t. And let us say the perturbation amplitude is epsilon. So, therefore, h becomes h at any given instance of, or rather let me put it, h x t becomes h0 plus epsilon into f x t, and we neglect any possible higher order terms. So, essentially we try to find the stability of the solution by trying to check the stability of the thickness of the film by giving a small fluctuation around h is equal to h0, and this perturbation amplitude is sort of a gives us the extent of how the film, how to what extent the film thickness deviates from its equilibrium thickness H0. So, what we can do is H becomes H0 plus epsilon f x t, which is linearized of H around H0 using the simple Taylor series expansion. And therefore, if we now plug in this value of H into the equation here, okay, so now H0 is essentially a constant, and what you have is epsilon, and f is epsilon is also a constant. So, f is a function of x and t. So, this equation now in the linearized domain transforms to So, you can see that mechanically all the terms containing H have now been substituted with F, but it is very simple essentially. If you just want me to go into little deeper, a little step by step, just to clear your doubts. What we have is H is equal to H0 plus epsilon f x t. So, del H del t, del t of this whole thing, and what you since H0 is constant. So, del H0 del t is equal to 0. So, you are left with epsilon del f del t. Okay. Similarly, if you perform let us say a term like, you take a term like h x x x. Okay. So, you have h is equal to H0 plus epsilon f x t, you take h x. So, what you get is epsilon f x, because del h 0 del x again is equal to 0. H x x you get epsilon f x x, h x x x you get epsilon f x x x, or in other words del 3 h del x cube here, which is written in a compact form as h x x x, is epsilon del f 3 del x cube. So, that is essentially del 3 f del x cube. So, that is how you convert this equation into or this equation in terms of f h into an equation in terms of f. One might argue, what about h cube? Well, you can write h is equal to h0 plus epsilon f x t, then h cube becomes this whole thing cube, and so it is essentially h0 cube plus epsilon f x t, epsilon square plus epsilon f x t square plus f x t plus sorry, yeah. So, it's epsilon into epsilon square, then epsilon cube. I'm sorry for this expression. So, it's h0 cube plus h0 square, 3, the prefactor is there, epsilon f x t plus 3 h0 epsilon square f x t square plus epsilon cube f x t cube. Now, epsilon itself is a small perturbation, therefore, all these terms tend to 0. Okay. So, that is how you essentially get this h cube over here gets replaced with h0 cube. The only other thing is phi h is a nonlinear function of h, which if we expand, which we can write as phi h0 plus del 2 phi del h square evaluated at h0 into h0 minus h square into epsilon f and so on. So, if you neglect all the higher order terms, then you can get phi h is equal to phi h 0 as well. Okay, and therefore, you get to the final equation, which is let us write it again, which is f t minus 1/3 mu gamma Okay. Now, one can understand that the function f x t, the actual functional form is going to be crucial in determining whether the solution is stable or not, and therefore, we need to choose an appropriate perturbation function, which can sort of test the stability of a film. The logic here, very simply put, is that you pick up a or choose a function which sort of can have the maximum destabilizing influence on the stability of a film. So, idea is that if any film is stable against the worst type of a perturbation function, worst in the sense that it has the maximum potential to damage or destabilize the film, then for any other type of perturbation or fluctuation, the film will definitely be stable. Or let me put it again. So, you pick up a perturbation function f, which is a function of x and t. We pick it up in such a fashion that it is going to be most difficult in terms of the stability of a film. So, if it destabilizes the film, it is perfectly fine. So, in real setting, the film is likely to destabilize. There are possibilities that it might not destabilize, because the function we are going to choose, the functional form we will again qualitatively discuss, is such. But if a film is found to be stable against this perturbation function we are picking up, then the logic is that this is the worst type of worst possible destabilization that is possible at the interface. But since it can sustain or withstand this type of a perturbation, then it is going to be stable against any other form of perturbation, because which is going to be milder. So, this is what is known as the concept of linear stability analysis, and is routinely used in various branches of science and engineering. It is a very standard mathematical procedure, which why the word linear stability analysis, because what you are doing is that you are taking a nonlinear differential equation and you are linearizing it with a perturbation function around a mean film thickness H 0, or any mean solution for that matter, to be general, to put it in general terms, and then checking its stability. So, what we do, we pick up a perturbation function which is repetitive in space and exponential in time. This is the type of a perturbation function we pick up. Let us say the functional form we take is f x t is sin k x into e to the power omega d. So, essentially this sin k x is repetitive in space, and k corresponds to different wave number. E to the power omega t takes care of the exponentially growing with time part of the perturbation function. So, k is the wave number, omega is the growth coefficient, and k can have all values from 0 to infinity. So, essentially it is a linear superposition of all modes of a Fourier series. So, considering this functional form, or corresponding to this functional form of this is the equation, like to have it in place. So, based on this, what we can find out is our f t is equal to and now, this is simple mathematics. You can just find out up to the del 4 f del x 4, because you will be needing it. You already have f x x x and another derivative f h. So, you need up to this particular term. So, this now also what you can do is that now that everything has been sort of linearized, you can sort of subsequently work on this expression. So, this now becomes gamma f x x x x, and so del phi or phi h 0 f x x into h 0 cube is equal to 0, okay, because this is now a constant now. It is no longer a function of x, because you have evaluated that at h is equal to h 0. So, once you have this expression, so out of this expression you will essentially be needing these three terms, this one, and this one, which eventually you will substitute here, here and here. So, once you do that, what you get is omega sin k x e to the power omega t minus 1 by 3 mu minus gamma into k to the power 4 sin k x e to the power omega t plus phi h 0 into minus, sorry, minus will come, yeah, it is there, minus k square sin k x e to the power omega t h 0 cube is equal to 0. So, from this step to this step it looks a little biggish, but really does not matter. All what we have done, we have substituted f t, we have substituted f x x x x, and we have substituted f x x. So, if you do that, what comes out is sin k x e to the power omega t, sort of you can cancel out from both the sides, and what you are left with is okay. Therefore, now if we use the expression of phi is equal to a divided by 6 pi h cube, considering the attractive van der Waals interaction, we can calculate the phi h 0 is equal to minus a divided by 2 pi h 0 to the power 4. So, if we plug in that expression, what we are left with is omega is equal to h 0 cube by 3 mu into a divided by 2 pi h 0 to the power 4 k square minus gamma k to the power 4. Now, this is what is known as the characteristic equation, and this is also very interesting now. See, we have taken the form, the functional form of the perturbation equation to be sin k x into to the power omega t. Now, this, so what is this? This is the surface fluctuation or the perturbation you have taken. Now, in order for the film to become unstable, as we have discussed in some of our previous classes, that the what has to happen is that these interfacial fluctuations should grow, okay, and then the amplitude of the qualitatively, this we have discussed. So, it becomes possible only when these interfacial fluctuations grow and sort of the amplitude of the growing fluctuations match that of the film thickness, then only one can argue that the film has ruptured. So, from this perturbation function, a growth of this amplitude is only possible. So, the amplitude, the growth of the amplitude when omega is greater than 0. Okay. If omega is less than 0, then what is going to happen, that with time this term is going to tend towards 0 and the perturbation is going to die down. In physical terms, what that means is that we know that these fluctuations are always opposed by surface tension. So, in that case physically a negative omega would mean that the strength of your attractive van der Waals interaction or the destabilizing force to be more general was not strong enough to overcome the stabilizing influence of surface tension. Therefore, from this, using this perturbation function, the film can only become unstable. Okay, the condition of instability of a film now turns out to be, or let us use a fresh sheet. Okay. Now, based on the concept we discussed here, okay, film can only become unstable when omega is greater than 0, right. Therefore, here also let us now examine the expression of omega carefully. You see, H0 is a film thickness, mu is the viscosity. So, these two are always positive. Okay. So, therefore, this prefactor H0 cube by 3 mu is always positive. Now, there is also another interesting thing that is hidden here, which we will discuss later. K we know is any real number, okay, or k is any integer. So, irrespective of whether k is positive or negative, both the terms are positive. Okay. Gamma is surface tension, it is again a positive quantity. We are talking about a film that is exposed to air. We are not talking about any interfacial tension, and we have always argued that the surface tension is always positive. Therefore, this term, since it has a negative sign, is always going to be negative. This multiplied by a positive number, so this is always going to be negative. K square is positive, H0 to the power 4 is also positive. So, the only way omega can be positive is this first term has to be positive. Only then this term is positive and this term is negative. So, if the magnitude of this particular term is now higher than the magnitude of this particular the second term, then only omega can be positive. Therefore, now we clearly understand the condition of film instability based on attractive van der Waals interaction is A greater than 0. So, A has to be higher than 0. Okay, this is number 1. So, for any system where effective Hamarkar constant is negative, then this term is negative, this term is also negative, therefore, the film is unconditionally stable. Further, you see, so in this expression, this is the potential destabilizing term which arises from van der Waals interaction. This is the stabilizing term, and we have always argued that whenever you have the surface fluctuation, surface tension opposes the growth. So, here it is, you can see that the term to which the surface tension is associated, it is the stabilizing term. Other thing is, you see that in the prefactor viscosity is at the denominator, which means that higher is the magnitude of mu, lower will be the value of omega. but mu cannot influence the sign of omega. That is, the rheology of the system or the viscosity of the system only can influence the dynamics, but cannot influence the stability of the system. These are important findings that comes out from linear stability analysis. The only other remaining important thing is that if you now look at the expression for the characteristic equation, again you can find out the mode at which the growth is fastest by setting del omega del k is equal to 0, and which gives you the fastest growing mode. So, in this class we will stop here, and we will pick up from the fastest growing mode in the next class and get an expression for the instability wavelength as well as the number density of the features that comes from the linear stability analysis, and then move on to some real experimental sequence of thin film dwetting, polymer thin film dwetting. Thank you.